Uranus drifts through the outer darkness like a silent anomaly, a world that appears almost lifeless at first glance. Its pale blue-green color, featureless disk, and distant orbit have earned it a reputation as the solar system's ghostly outlier. Yet beneath that calm, washed-out appearance lies a planet that defies expectation. Uranus is not dead. It is not simple. It is one of the most physically strange and scientifically revealing worlds ever discovered. To call it the solar system's pale corpse is to misunderstand the nature of what we are seeing. It is pale because of methane filtering red light from the sun. It is quiet because it receives so little solar energy. But it is not empty. It is a frozen giant holding secrets about planetary formation, atmospheric chemistry, magnetic chaos, and the violent history of our cosmic neighborhood. Discovered in 1781 by William Herschel, Uranus was the first planet found with a telescope. Until that moment, humanity believed the solar system ended with Saturn. The discovery doubled the known size of the planetary system overnight. Uranus orbits at an average distance of about 2.9 billion kilometers from the Sun, nearly 20 times farther than Earth. At that distance, sunlight is 400 times weaker than what reaches our planet. The Sun appears as a bright star rather than a dominant disk. Temperatures in the upper atmosphere drop to around minus 224 degrees Celsius, making Uranus one of the coldest planetary atmospheres in the solar system. Its classification as an ice giant distinguishes it from the gas giants Jupiter and Saturn. While Jupiter and Saturn are composed mostly of hydrogen and helium, Uranus contains a higher proportion of what planetary scientists call ices. These include water, ammonia, and methane, not frozen in the everyday sense but existing in exotic high-pressure forms deep within the planet. Beneath its atmosphere lies a thick mantle thought to consist of supercritical fluids, a strange state of matter that is neither liquid nor gas. Deep still, at extreme pressures and temperatures, these materials may form ionic oceans where water molecules break apart into charged particles that conduct electricity. The most striking feature of Uranus is its axial tilt. The planet rotates on its side with an axial tilt of approximately 98 degrees. In effect, Uranus rolls around the Sun rather than spinning upright like most other planets. Each pole experiences about 42 years of continuous sunlight followed by 42 years of darkness. This extreme tilt likely resulted from a catastrophic collision early in the solar system's history. A massive impactor, perhaps twice the size of Earth, may have struck Uranus, knocking it sideways and altering its internal structure. The aftermath of that collision could explain why Uranus emits surprisingly little internal heat compared to Neptune, its similar-sized neighbor. Unlike Jupiter and Saturn, which radiate more energy than they, received from the Sun, Uranus emits almost no excess heat. This has puzzled scientists for decades. One hypothesis suggests that the ancient collision disrupted internal convection, trapping heat deep inside the planet. If so, Uranus may be thermally suppressed, a giant world whose internal engine is partially stifled. That lack of heat may contribute to its relatively subdued atmospheric appearance, at least when observed in visible light. Yet Uranus is not truly calm. Observations in infrared and near-infrared wavelengths reveal dynamic cloud structures, storms, and wind systems. Wind speeds can exceed 900 kilometers per hour. Methane in the upper atmosphere absorbs red wavelengths of sunlight, giving the planet its pale cyan coloration. Below the methane layer are clouds composed of hydrogen sulfide and possibly ammonia. Seasonal changes driven by the extreme axial tilt cause atmospheric activity to intensify as different hemispheres receive prolonged sunlight. The magnetic field of Uranus is another anomaly. Unlike Earth, whose magnetic field is roughly aligned with its rotational axis, Uranus possesses a magnetic field tilted about 59 degrees from its rotation axis and offset significantly from the planet's center. This creates a wildly asymmetric magnetosphere. As Uranus rotates, its magnetic field sweeps through space in a corkscrew motion, producing complex interactions with the solar wind. The likely source of this unusual field lies in the conductive ionic layers, within its mantle, where charged particles circulate in patterns different from those inside terrestrial planets. In 1986, NASA Voyager 2 spacecraft performed the only close flyby of Uranus to date. It revealed a system of thin, dark rings and at least 10 new moons. Uranus has 27 known moons, many named after characters from the works of Shakespeare and Alexander Pope. These moons range from small irregular bodies to larger spherical worlds such as Titania, Oberon, Umbriel, Ariel, and Miranda. Miranda in particular displays dramatic geological features including towering cliffs and patchwork terrain, suggesting a history of tectonic disruption and reassembly. The ring system of Uranus differs from Saturn's bright icy rings. Uranian rings are narrow and dark, composed of larger particles and less reflective material. Their origin may involve shattered moons or debris from collisions. The rings are confined by small shepherd moons whose gravity maintains their sharp edges. This delicate gravitational choreography illustrates the subtle forces shaping even the faintest structures in the outer solar system. Uranus occupies a crucial role in planetary science because ice giants appear to be common in our galaxy. Observations of exoplanets reveal that planets between Earth and Neptune in size are among the most abundant types in the Milky Way. Yet our understanding of ice giants is limited. By studying Uranus, scientists gain insight into planetary systems beyond our own. Composition, structure, and atmospheric chemistry serve as natural laboratories for understanding distant worlds orbiting other stars. The pale appearance of Uranus also challenges assumptions about activity and vitality. In visible light, it may look uniform and bland, but advanced imaging techniques have revealed transient storms and bright cloud features. In recent years, powerful telescopes have detected seasonal changes as the planet approached equinox. As sunlight shifted toward the equator, atmospheric dynamics intensified. What once seemed static proved to be evolving. One of the most fascinating theoretical possibilities inside Uranus involves the formation of diamonds. Laboratory experiments simulating the extreme pressures within ice giants suggest that methane may decompose, allowing carbon atoms to crystallize into diamonds that then sink deeper toward the core. This so-called diamond rain remains hypothetical, but it illustrates the exotic chemistry possible under such conditions. Despite its distance, Uranus influences the architecture of the solar system. Its gravitational presence helps shape the Kuiper belt and may have contributed to the orbital evolution of other planets during the early chaotic phase of planetary migration. The discovery of Neptune itself resulted from perturbations in Uranus's orbit. Astronomers analyzing irregularities in its motion predicted the existence of another planet. In 1846, Neptune was observed near the predicted location, marking a triumph of mathematical astronomy. The exploration of Uranus remains incomplete. A dedicated orbiter mission has been proposed to study its atmosphere, interior, magnetic field, rings, and moons in detail. Such a mission would answer fundamental questions about planetary formation, heat transport, and magnetospheric physics. It would also clarify why Uranus differs so markedly from Neptune despite their similar size and composition. Calling Uranus a pale corpse reflects how human perception can misinterpret subtlety as absence. The outer solar system operates on slower timescales and under weaker sunlight. Processes unfold gradually, often invisible without sensitive instruments. But absence of spectacle does not equal absence of power. Uranus embodies the quiet complexity of planetary evolution. Its sideways rotation records ancient violence. Its suppressed heat hints at internal restructuring. Its magnetic chaos reveals exotic conductive oceans. Its moons preserve geological history shaped by tidal forces and impacts. From a broader perspective, Uranus expands our understanding of what planets can be. It demonstrates that planetary systems are not uniform arrangements but diverse collections shaped by collisions, migration, chemistry, and gravity. The serene blue disk conceals layers of physics that challenge and refine theoretical models. In studying Uranus, scientists refine equations describing fluid dynamics under extreme pressure, magnetohydrodynamics, within ionic mantles and radiative balance in cold atmospheres. The pale glow of Uranus also invites philosophical reflection. In the darkness beyond Saturn, where sunlight fades and temperatures plummet, the planet continues its slow 84-year journey around the sun. Each season spans decades. Storms develop and dissipate across years rather than days. The rhythm of Uranus reminds humanity that time is relative to scale. What seems inert may simply operate on a different clock. The phrase solar system's pale corpse captures the emotional impression of distance and cold, but science reveals animation beneath that stillness. Uranus is not dead matter drifting aimlessly. It is a gravitationally bound, chemically active, magnetically dynamic world shaped by billions of years of cosmic evolution. Its very strangeness makes it essential to understanding the range of planetary possibilities. As telescopes improve and missions are planned, Uranus stands as a frontier. It challenges observers to look beyond first impressions and to investigate the mechanisms hidden within faint light. The pale surface is a veil. Beneath it lies a layered structure of hydrogen, helium, water, ammonia, methane, and possibly crystalline carbon. Beneath the quiet exterior lies a history of impact and transformation. In the end, Uranus teaches that subtle worlds can hold profound lessons. It shows that planetary science is not only about blazing storms like Jupiter's Great Red Spot or the spectacular rings of Saturn. It is also about deciphering quiet enigmas. Uranus may appear ghostly, but it is a living participant in the gravitational dance of the solar system. Its orbit, tilt, magnetism, and chemistry all contribute to a deeper understanding of planetary formation and cosmic evolution. The pale light of Uranus does not signify death. It signifies distance, it signifies methane absorbing red sunlight, it signifies a planet whose energy budget and seasonal cycle differ from our own. When examined closely, the supposed corpse becomes a complex ice giant whose mysteries continue to shape scientific discovery. The interior of Uranus remains one of planetary science's most compelling puzzles. Standard models suggest a small rocky core surrounded by a vast mantle of water, ammonia, and methane under immense pressure. In these conditions, water does not behave as a familiar liquid. It likely exists as a superionic phase where oxygen atoms form a crystalline lattice while hydrogen ions move freely through it. This superionic water may conduct electricity efficiently, contributing to the planet's unusual magnetic field. Laboratory experiments using high-pressure shock compression have begun to reproduce these states of matter, bridging theoretical predictions with measurable physics. The importance of Uranus extends to comparative planetology. By contrasting Uranus and Neptune, scientists seek to understand why two similarly sized ice giants differ in thermal output and atmospheric activity. Neptune radiates significantly more internal heat and exhibits more visible storm systems. Uranus, by contrast, appears thermally muted. Determining the cause of this divergence may reveal how initial conditions, impacts, and compositional gradients shape planetary evolution over billions of years. Future exploration promises transformative discoveries. An orbiter equipped with atmospheric probes could directly sample the composition of Uranus's clouds, measure isotopic ratios, and determine the abundance of noble gases. These data would constrain models of solar system formation, revealing whether Uranus formed closer to the Sun before migrating outward or accreted material in its current region. Detailed mapping of its gravitational field would clarify internal mass distribution, while magnetometers would refine understanding of its dynamo process. The narrative of Uranus ultimately shifts from the imagery of lifelessness to a portrait of complexity concealed by distance. It stands as a testament to the diversity of planetary outcomes. Not all giants blaze with dramatic storms or radiant heat. Some evolve quietly, preserving within them evidence of ancient collisions and exotic chemistry. In its pale glow lies a record of the early solar system's violence and creativity. To view Uranus merely as a distant blue sphere is to overlook the intricate physics governing its structure and motion. Its sideways spin challenges notions of planetary stability. It's suppressed. Luminosity invites investigation into heat transport. Its magnetic asymmetry reshapes understanding of dynamos. Its moons reveal geological diversity in environments far removed from sunlight. Each aspect contributes to a broader comprehension of how planets form, change, and persist. The solar system's pale corpse, when examined with scientific clarity, becomes a living archive. It carries the memory of impact, the signature of chemical transformation, and the dynamics of magnetic turbulence. It invites renewed exploration and deeper inquiry. In the silence of the outer darkness, Uranus continues its measured orbit, not as a relic, but as a vital piece of